Hello, everyone, and welcome to another Zephyr webinar, this time entirely in English. If you have followed our previous webinars, you may notice that we usually present in Spanish. However, with the goal of sharing knowledge with a wider audience, we decided to host this session in English to reach more developers around the world. My name is Diego, and for the next 40 minutes, I'll be talking about how to get started with Ethernet in Zephyr. As usual, we'll go through practical, easy to follow examples that you can replicate later or use as a foundation for your own projects. So at the screen, you are seeing the website of the Microelectronics. The reason is because in this webinar, I'll be using an STM32H573i discovery kit, which features a Cortex M32 processor and also includes an onboard Ethernet variables. You can see in the image that this is the board that I'm using right now. So right now it's connecting to my computer through OpenOCD. And at the moment I have disconnected the Ethernet cable. But for the purpose of the webinars, we are going through some examples. So will see how to the same Zephyr networking stack can detect when we plug and unplug the Ethernet cable. So you want to learn more about this board, you can check its official documentation at the websites, but also you can find some very good information about how well supported is this board in Zephyr. Among the information that you can check at the Zephyr official website for these following boards is the amount of low-level drivers that are currently supported. And you can see in this part, Ethernet is fully supported by the following bindings, or sometimes we can call it low-level drivers. Let's talk about a little bit about the Zephyr networking stack. On the following page, you can see a detailed diagram of the different layers that make up a Zephyr networking stack, as well as the protocols supported at each level. This diagram shows how Zephyr organizes networking architecture in layers, from the application layers, sockets, down to the IP layers, IPv4, IPv6, transport protocols like TCP, UDP, and finally the L2 link layer. You can see in this part that Zephyr support multiple L2 technologies, or as I like it to describe it, multiple ways to access the physical medium. This includes Ethernet, Bluetooth, Wi-Fi, and even CAN. So you had experience working with CAN, you maybe wonder how this can be supported. Well, there is something that is called socket CAN. Since we have limited time today, we will focus especially on the Ethernet L2 layer, the network interface layer, and TCP sockets. So hopefully we'll have enough time to explore this properly. First and first, let's start with the fresh Zephyr projects. So you can see at your screen that I'm using Visual Studio Code. I'm also using a Docker container, which has all the tools that I'm going to need for these webinars, such as the West Meta tool, the compiler, which I'm using a ARM GNU compiler, and OpenOCD to flash my board and also to debug in case of necessary. All right. We can also see in this window that this is the minimum project structure that we need on Zephyr. So we also has a folder for testing, but we're not going to use it on the webinar, so we can safely delete it. So you can see there is a West manifest. That is very simple. We are using 4.3 of the Zephyr revision. We had our CMake, our file prgconf to enable or disable the different pieces of the networking stack that we're going to need. Right now it's empty. And of course, our main file main.c. So let's proceed with building. Just to verify, all right, let's build from scratch. Just to verify everything is working according to expected. And as we can see, everything is pretty much fine. It makes sense because at this point, we basically don't have anything implemented yet. So we're going to start from scratch, all right? Good. So let's open the file prgconf because we are going to write some we're going to enable several pieces of the networking stack that we're going to need. So through the webinar, you're going to see me copy paste from some snippet that I specifically prepared for these webinars in order to avoid as many typo mistakes that I could have when writing the code manually. So you're going to see me do this and copy pasting, you know? All right, these are the first options that we're gonna need in order to start working without networking. First things first, we need to enable the networking stack itself. We're going to work with IPv4. I think by default IPv6 is the one that is enabled, but in our case, we're using Ethernet, and for a simple example, IPv4 is more than okay. So another important thing that we need to enable is the Ethernet driver, you know, and also, and since I'm using an STM microcontrollers, we need to use the a specific help driver from ST. So with these options, I'm gonna save the files, and now I'm gonna move to the main.c to write some code right here. So I'm gonna go back to my snippets that I prepared for these sessions, and I'm going to describe what did I write in here. So the first thing that we need to do is to include the Ethernet header. So that's why we're going to use the Ethernet. The next things to use is to basically call the net underscore if underscore get underscore default function to obtain the network interface that we are planning to use. These functions will return a pointer to an structure of type net underscore if. If is for interface, okay? Which represent a network interface instance in Zephyr. In our case, we are only using one interface, Ethernet. So it is safe to retrieve the default one, right? However, keep in mind that a Zephyr system can have multiple interfaces, like the one that we mentioned before, like Ethernet, Wi-Fi, even Bluetooth or CAN, or maybe you can have more or multiple instances of the same type, all right? Okay, so we're gonna use the return pointer because this is returned to an instructor that is this is the very common mechanism that it is using Zephyr to configure, control, and interact with the network subsystems through the network interface API. All right. So, in the following example, or for the first examples, what we're gonna do is to use this pointer to the structure, to our interface structure, to retrieve the name of the interface that we are using. Plus, why not, as an exercise, a MAC address. First, I'm gonna write these auxiliary functions that will allow me to print our MAC address, our default MAC address, in a more friendly way. So it's basically a series of print case with a colon in between of each of the numbers. All right. So you can see that I run into the code of functions that will print the interface name that is obtained through the pointer to the structure that we just get on the following line. And then we're gonna pass the same interface, the same pointer to an auxiliary functions to friendly print the MAC address. I'm gonna save the code and I'm gonna build from scratch again. All right, it's gonna take in a few seconds. Once it's ready, I'm gonna proceed to call OpenOCD through my VS Code debugger plugin. Thinking is working, and it's working now. So one of the things that I'm going to do is I'm gonna open serial monitor in order to see the print messages. So I'm gonna open this and I'm gonna run my code. There you go. So we can see on the serial port the name of the interface, that is of course Ethernet, because it's the one that we are using and configuring, and the default MAC address that is assigned. All right. Okay, printing this information is a simple but very effective way to confirm several things. Among them is Ethernet driver was properly initialized, network interface is registered, and the hardware MAC address has been correctly configured. This is the first thing that you will need to do when you are starting to configure your networking stack. Okay, if this doesn't work, it doesn't matter if you continue, because the rest of your code is just not going to work. This is very simple step that will guarantee you that the stuff that you're doing are starting to work correctly. All right. So there are several ways to configure a MAC address in Zephyr. It can be provided by the hardware. For instance, it could be a factory programmed on the register of the physical interface that you are using, or maybe you are using an external module, or maybe or the intention is to record the MAC address in a E-square EEPROM external memory or in a flash memory after the end of line of the production of your models. So Zephyr offers different ways to do it. Okay, so you can even set dynamically the MAC address on your code. But for now, we'll keep it the default configuration, and let's move forward to a more interesting stuff. All right. So by the way, and just to clarify, this is the board that I'm using, and as you can see, Ethernet cable is not connected yet. All right. So what we're gonna do is I'm gonna stop the debugger, right? I'm gonna write some code, an infinite loop. Let me go to my snippets. Let me add this infinite loop, right? It's a simple while loop on my main thread. Uh-oh, something was wrong with my keyword. There you go. So it is a simple while loop that I'm using another API functions just to interrogate if the network interface is up or if it's down. All right. So in practice, the Ethernet drivers detects links events such as carrier on, that is basically when you connect the cable, or carrier off when you disconnect the Ethernet cable. Based on those events, the network interface changes its states. What we're doing basically on our loop is periodically we check the interface. And what we're gonna do is simply to print a simple message. Link is up or link is up. That will tell us if the cable is connected or not, okay? So as you can see, I declare a few lines here. There are a few variables that I'm gonna place right here. There you go. So let's build again. And notice that we didn't disconnect our serial port. So when the terminal indicates that we are ready to debug again, I'm gonna run the code. All right. So let's clean the screen. Let's run the code again. We're running the code again, and as you can see, what it's telling me, link is down, and that's because you can see in my board, it's not, the cable is not connected yet. So what I'm going to do is I have this Ethernet cable, so I'm gonna connect. By the way, the other side of the cable is connected to my router. So you can see the link in the indication of the link is up. I'm gonna disconnect it again so you can see link is down, detection. Let me hop in the cable again, and link is up, detection. So with this very small code, we are also verifying that our board is actually detecting an event, a network event. This is important. We are detecting a network event, right? With this very example, like I explained before, we can notice the Ethernet hardware is working correctly. Okay, that is good. The driver is properly initialized, and the networking stack responding to link state changes. So good, so well, right? Okay, but doing it this way can be a little bit, well, you know, this is important. Okay, you can always, in your application, you have to monitor when the cable is connected or disconnected. But while polling the interface state inside a loop works, in the Zephyr network, it can provide a much better and more efficient mechanism to handle this with event-driven callbacks instead of continuous polling, right? As usual, in Zephyr, we're going to define a callback function with the correct prototype, okay? So let's starting writing the code. So again, I'm gonna go through my snippets and you're gonna notice that I'm going to include another header. I'm gonna explain a little bit more why we need this file.h. Okay. The next thing that I'm going to literally copy paste from my snippets is a function, is another auxiliary function. This is the functions that I'm going to use as a callback. Okay, it has a specific prototype according to the Zephyr documentation. In here in this call, when an event is detected, I'm gonna print a couple of messages when the cable is connected and when the cable is disconnected, just how it did right here. So I'm not gonna use these variables anymore. So let's remove it. Let's stop the code before something happens. And what I'm going to do is basically call a function to register the callback. I'm going to remove the infinite loop because we don't need it yet. But one of the first parameters that this function is requesting is a physical device descriptor. Okay, so here we are using a network interface descriptor, but in this we need a physical device. You know, they call it PHY device is basically what is going to make the interface between our microcontroller and the physical medium, right? It's connected, is the microcontroller internally has its own peripherals, but externally there is an external module. And this is a lower layer in the networking stack, lower than the interface layer. So it's pretty much detecting actually the cable connection and disconnections through callback, right? So I'm gonna clean up my terminal again, and I'm gonna proceed to, this time I don't need to build from scratch, to make it faster. So I'm gonna run my code again, and go to serial monitor. Okay, once the code is ready, down. You can see it also, I can get the name of the physical device. This name is obtained from the device tree, all right? So depends on the board that you are using. It is quite possible that this name changed a little bit, right? It's detecting that the cable is connected, so I'm gonna disconnect it again. Detects the disconnection, so I'm gonna connect it again. This is a much better way to detect when the cable is connected or disconnected, all right? But let's clarify a few things before to continue again, right? Here we are detecting the event at the lowest layer, okay, at the physical layer. The PHY hardware has the responsibility to detect when the cable is physically connected, there is valid electric signal, and the link negotiation speed, the duplex, etc., succeed. All right. So when we are using this, let's say, method, we are accessing the physical device abstractions, right? So this is something that is very Ethernet specific, meaning though, if you are using another medium, another way to access the medium like a Wi-Fi or CAN, this is not going to work. You're gonna need to use another set of functions, right? So what it's recommended is to detect this event. Well, I mean, at the end of the day, you're gonna at some point or some moment, maybe it's more convenient on your code to detect when the cable is connected or disconnected from the physical layer, you know. But maybe what you want to do is to actually manage this through some networks events, yes, from the upper layer, just like we did in our previous code. So let's do this. Let's do what we did before, but this time using callbacks. Okay. And the first things that we need to do is to add some extra configurations. So we need to enable the networking management event. This will allow us to detect several things. You know, among them is of course when we hop in and hop off the cable to our board. Right. So what we should do in our main code. So we're gonna remove these functions we wanna replace for another callback, right? Another callback that belongs to the upper layer, to the interface layer. So I'm gonna use the same name for the callbacks. I'm not gonna change it, but notice the prototype is completely different. It accepts a set of different parameters. Among them, the interface pointer, and it also will accept a management event, but basically it's a variables that gonna let you know that you are going to use inside the functions to check the events of your interest. All right, but there's several events that you can detect. You can control click on the code, and you can see right here there are several events that are defined, right? We can also detect IPv6 address assignments, and IPv4 address assignments, and several ones. All right. You can check the documentation. You can check the Zephyr networking code, etc. But right now, what we are interested in only when the network is up or the network is down, right? That it will translate it for our specific case when the cable is connected or disconnected. So I'm gonna save my code, and in here, this line of codes are not gonna need it anymore because we are not using this layer. What we're gonna do is to use a set of macros. First things first, I need to declare an instructor. I'm gonna put inside main, problem, and what I'm going to use is to call a couple of macros that will help me to register the callback right here. We're going to tell it, all right. So this is the function that we're going to use as a callback, and this is the event that you will have to detect. Okay. So then I'm going to add the event. These are not functions. These are macros, by the way, all right. And according to the Zephyr official documentation, so maybe they can change it a little bit in the futures. But right now, these are macros. So let's build our code again. Let's clean up our terminal window, and let's go for since we modified our kconfig configuration. I always suggest to build from scratch. It's not necessary, but let's do it in order to avoid any undesirable surprises. All right, so let's run the code again. The cable, notice the cable, it's already connected to the board. Okay, the text again, one more time. The cable is connected. I'm gonna disconnect it. Cable is connected. I'm gonna connect it again and again. It detects the cable is connected. All right. So at the moment, what we're doing is very simple, you know, but it's a very easy way to debug the most simple things in our networking stack. So it's time to move forward. So for network communication to occur, we need something more than the MAC address. We need an IP address assigned to our interface, to our network interface. Remember, the MAC address is assigned to the physical device while the IP address is assigned to the interface, right? The simplest way to assign an IP address is manually, and we can achieve this in Zephyr using a function from the networking interface layer, right? Zephyr provides an APIs that allow us to add or remove IP addresses. Uh, a really good practice is to assign an IP address when the interface goes up, meaning right here, okay? And also you can remove the assigned IP address when the interface goes down, meaning right here in the same callback function, all right? Okay, let's do this. Let's here inside this function, let's assign an IP address. First that you need to do is to declare a variables that is going to help you to set up the values. You can see this is the variables that we're going to use is actually on a structure, and inside the structure there is a union because there are several ways that you can use in order to set up, in my particular case, this IP address, no, 192.168.1.100, right? The format and is big endian. So what does it mean that is big endian? Well, basically, the most significant octet of the IP address goes into the less significant byte, right? In the array. This is important. Otherwise, you will be setting the wrong IP address. So what we need to do next, well, it's very simple. You only need to call a function to add this particular address, all right? So we're gonna set an address manually, okay? You're gonna pass this parameter, which is the interface, and the actual address you put in right here. So what's gonna happen when the cable is disconnected? Well, you can remove the address that you just assigned, right? So I'm gonna save my code again, and I can build and compile a code, but nothing is gonna change on the message that I'm seeing in my serial port. So what I'm going to do is to add another callback, right? Because uh, we are going to have another event, right? So we have an event where the network is up, but at the moment that we assign an IP address, we're gonna have a different event, which is the event when an IP address is accepted and is actually assigned, all right? So instead of running the code, let me register another event, right? So I'm gonna add another variable right here. Okay. Again, it's same structure, has to be static. But I'm gonna call it management underscore IPv4 because we are going to detect IPv4 events, right? So I'm gonna register this new callback for this new event. I'm gonna save it right here, and I'm gonna use another different functions. We can use the same one, all right? We can use the same callback, and right here using the variable, we can detect this new event. But let's do it in a different callback, all right? Just for simple demonstration purpose. So I'm gonna copy paste this. I'm gonna place it right here. All right. So far so good. I'm gonna explain a little bit about what's going on in this new callback. Notice that we are not using an if to detect if the events that calls the callback is the one that we are looking for, just for simplicity. But in a real world, you need to do this in order to avoid spurious event detections different than the ones that you are intended to do. All right. Uh, what I'm going to do inside the callback is basically to call several API functions to get the IP address, the subnet mask, and the gateway mask. All right. I'm gonna use these particular functions, net underscore addr underscore ntop. All right. And I'm going to pass uh, some elements in the structure of iFace. All right. I'm gonna store it in a buffer larger enough to hold the information that I'm going to receive that is going to be on a string that later on I'm going to print. Okay, I'm going to print the IP address, the netmask, and the gateway. I'm going to save my code once again, and I'm going to build it one more time. I'll cross my fingers. Okay, it's compiling, and let me run again. I'm gonna disconnect the cable just because. Why not? Okay, Ethernet cable is disconnected. Let's run the code. Nothing happens, so I'm gonna connect the cable, and voila. It detects that the cable has been connected, and also it's giving me the IP address that is assigned, the one that I'm assigned manually in this callback using this interface. No, that also is giving me the netmask and the gateway, right? So if you disconnect, well, there's nothing gonna happen. There's only the message telling you the link that cables disconnect. Now I'm gonna connect it again, and as you can see, the same IP address is assigned again. Let's stop the code. Let's go back to our main to do some more interesting stuff. So some of this more interesting stuff is instead of manually assigning an IP address, we can configure the interface to obtain one dynamically using a DHCP client. All right. This DHCP client is the ones that we need to run in our microcontrollers in order to receive that information, that IP assigned by a DHCP server that is potentially running. Well, in my case, is running on my router. All right. And this scenario is the ones that basically you're going to use when you are going to put your device on a larger network that already has connected to Ethernet or to some other modules through another device like a router or something else. All right. So setting a static IP address is fine for testing or for a small local address. It will depend on your applications, but the usual way to connect your device to Ethernet is, or the usual way to assign an IP address to your Ethernet connected device is through a DHCP server. Okay, like usual, and maybe you already guessing, we need to set in our key config files new options. All right. So, so we enable so many things because the networking starting Zephyr is larger enough to consume a lot of flash memory, flash and RAM memory. But it's divided in different several pieces that you need to enable. So in this way, you are going to actually enable the ones that you're gonna need. So okay, so it's pretty much you are going to be assembled through different steps. Uh, Depends on your replications, the networking stack that you're going to need. All right. So once that we are telling the that we are going to use the DHCP servers, what we're going to do is we don't need this callback anymore. This one, where sorry, we don't need these functions, right? So let's remove these functions because we are no longer assigning an IP address manually. Neither need these variables inside the functions. We want to keep the same the callback just because for all right. So what else I need to do? All right. So what I need to do right here after register the callback, I'm gonna call a function, call it net DHCP P4 because I'm using IPv4 IP addresses. In case you're using IPv6, just change the 4 for the 6. Underscore start. And the only parameter that I'm gonna need is the pointer to the interface structure that we are using in our code, right? Okay, just let me verify if I'm not missing anything else. No, I'm not. So let's clean up a little bit of code. Remember, this is the only line that we added in order to use the HCP. And we remove from this callback the assignment of the static IP address, right? Let's clean out the terminals. So let me go back and build from scratch because I set some new options in my key config file. All right, then like it's working as expected. All right, already built. Now let's run the debugger again. Okay, code is ready to run. Cable is connected to my board. Ah, sorry, I was monitoring. So what I'm gonna do is to pause, reset, apply a reset, and run again. Okay, the cable is connected. It's gonna take a few seconds. Remember, there is a negotiation between the client and the server. So in order to server send the new IP address, the new netmask, the new gateway address to our device. So it's gonna take a few seconds. It's not going to be something that immediately is going to happen. So let's disconnect the cable and connect it again. We take the cable disconnected. It's gonna wait like a few seconds, and voila, we have assigned it to IP address. So this is basically the method that you are going to use most of the time, right? And it's as simple as calling these functions that you see right here, right? So let's go for a more interesting. So far, what we're doing here during the webinar is pretty basic setup of networking stack. All right. But let's go to a upper layer in the networking stack. Let's go and use a TCP socket that is going to allow us to establish communications between two devices to send actual data to one device to another one. So we're not going deep into what a TCP socket is, since there is plenty information available on the topic, and sockets are not exclusive to Zephyr, right? In fact, Zephyr implements its socket API to be largely POSIX compatible. This means that if you already had experience working with sockets on platforms like Linux, the API will feel very familiar, actually. So the same concept will apply on creating sockets, binding them, listening, accepting connections, sending and receive data. You basically will feel like home. And these sockets, you can implement these sockets pretty much on any language or that you can use, meaning Python, C Sharp, Rust, you name it. All right. And as you are guessing, in order to use this socket, guess what? We need to add, well, we need to enable another set of kconfig options. So net sockets, POSIX API, and config net TCP. Remember, all of the trees are necessary, at least for the example that we are going to run. Okay. So before writing the code that we're gonna need, let's clean up a little bit what we have right here. So we're not gonna need to display the MAC address, all right? Neither we are going to need to detect when the cable is connected or not. Okay. Don't make mistakes. On your application, on a real world, you're gonna need it. But for these demonstrations, in order to simplify what we're doing, we are just removing them, right? All right, pretty cool. Now the code is simpler than before, right? Okay, so what I'm going to do is to create a simple function, okay? The simple functions to implement a very simple TCP client, right? So again, I'm gonna copy paste some code that is ready. Don't worry, I'm gonna explain it in a few seconds. So what we are going to do inside our function is basically to create a socket using the function socket. This is POSIX compatible. So I'm telling you is a TCP socket with this constant socket streams. I'm not in any extra flag. And what I'm doing here is to indicate what kind of socket is, all right? The port that is going to connect, that is a 9000, and the address of the device is going to connect. So this is important. This device that is well running the server is actually my computer, all right? And if we type IP add, so we can see the different network interface that I have on my computer. And my computer is connected to Wi-Fi, and the IP that is assigned is 192.168.141. This is the address that I'm going to use to communicate. And this is the one that I'm indicating right here. So all this information is stored in this variable, and I'm going to use these auxiliary functions in order to set from this address from n strings to a binary format. All right. There are several ways to do this, but let's go through this because always expressing the address in a string format is easier for us when we write and modify the code. So after the socket is created, you're going to call a function that is called connect. You indicate the socket that you're using and the data with the server address and port to connect. It is important to verify if the connection was done. Otherwise, we need to do something, right? In this case, because we are doing very easy example, we're just gonna print a message, and when connect successfully, we're gonna send a simple message to our servers. After that, if the connection was successful or not, we're just gonna close the socket, right? Something really simple that for demonstration purpose it is more than okay. So there is one include that you need to use in your code. That is the ones that allow to recognize the functions that you're using. All right. All right. So I'm going to call my auxiliary functions inside a where is ChatGPT when you need. All right. inside an infinite loop. So every 5 seconds, I'm gonna try to open a connection to a remote server, and I'm gonna, if it succeeds, I'm gonna send a message. All right. So something's wrong with this with my debugger. Don't worry, we're gonna build from scratch. I'm gonna clean out the monitor. Once it's compiled, I'm trying to run the code. Right. In the meantime, on my computer, I need to run the server, a TCP socket listening, waiting for connections. So I'm gonna do this using Netcat. Netcat is an utility, a networking utility that comes with my Ubuntu machine. I'm gonna run it, and I'll be listening on the. I'll be listening to all IP address, but more specifically on port 9000. Okay, so let's pay attention on this one. I'm gonna zoom in a little bit. Maximize this. Gonna minimize. It's listening. My application in my microcontroller is not running yet. And so I'm gonna run it again. I'm gonna restart just to verify everything is fine. The terminal port. Okay, the board is still connected to the cable. Oh, okay. One thing is missing. I'm really sorry. Okay, so as you noticed in the previous example, assigning an IP address from using the HCP protocol is not something immediately. So what we need to do is to wait, and we can do this in several ways. To keep it simple, what we're gonna do is to wait for 5 seconds. Okay. In reality, in real world applications, you're not going to sleep and wait until if after 5 seconds the IP was correctly assigned. What you're gonna do is to use another kind of synchronization mechanism, like for instance a semaphore. All right, it could be a semaphore between the the callback that indicates that an IP was successfully assigned to the rest of your applications, right? In our case, let's go for a more simple mechanisms. That is a delay. Well, in reality, it's not a delay, but we want to say it's a delay. Okay, I'm gonna clean up terminal, and again, verifying the socket TCP server is waiting. I'm gonna run my code. I'm gonna run the code again. Sorry, forgot to start monitoring. All right. So, I forgot to start monitoring the terminal, but as you can see right here on my computer, it successfully received the connection from my microcontroller from this IP. All right. And this is the message that is received. Let's do it again. Oh, well, let's verify on my application terminal that after that the TCP is closed. So what happened on my microcontroller? Well, it's telling me that the connection to the server just failed. All right. So I'm gonna open the connection again, but this time I'm gonna see what's going on the side of the microcontroller. We have the message connected to server. And on the side of my computer, we can verify a connection was received and the message also was received, right? So with this last example, we pretty much complete the webinar of today. But I think it's worth it to mention a few extra things. So I'm gonna close the terminal because I'm not gonna use it. I'm gonna display my project. So one thing that maybe you notice is that on our overlay file, we didn't configure anything. So we didn't touch any configuration on the hardware, all right? The reason is pretty simple. We are using an official board that is shipped with the Zephyr project. It is supported by ST Micro, and if you know this right here on my Visual Studio Code, we can go to Zephyr board. This one right here. That is this right here. So if you display the folder, inside the folder, you can see several configuration options that already comes with this configuration files. All right, the one that belongs to the device tree is these ones, and the most important ones that you should take into account for Ethernet connection is the node that is called MAC and the node that is called NDIO. Right here, you can see we are configuring, or there's already pre-configured the pins that connected to our network interface, physical interface. All right. The type of connections that we are going to use in this case is ARM-II. All right. And there is another node that you will need to configure it. So just imagine that you are working on your own board, on your own custom board. So you want to have access to these pre-configured files, but these are the ones that you have to configure. Okay. Special attention should be carried out. So maybe you are using a microcontroller from different vendors, then the name of the nodes are gonna be different, maybe quite different. So for instance, from NXP, Texas Instruments, Microchip, you name it. Where you can find this information, where these informations can be found on the official documentations. In Zephyr, it's very common that you take a look at where this node is declared. In the case of STN, these nodes are declared at, I think it's in the SOC definitions. Um, it's pretty messy to look for these definitions, but here we have. Okay, this is the MAC node being declared, and in these files, the compatible ones, you are going to look for the properties that you're eventually going to need to configure. So in Zephyr, you will always looking for the information stored in these YAML files. At the end of the day, those are YAML files with the information of the different properties that you're gonna need in case that you needed to configure. All right. So yeah, also worthy to mention that in the kconfig.devconfig, you can find also some extra keyconfig options that if you don't have these files, you will need eventually to place in your project keyconfig. All right. For instance, in our case, if we didn't have these files belonging to the board that is officially shipped with Zephyr, uh, we will need to add this option right here. All right. Otherwise, our Ethernet connections won't work. Okay, so time to say goodbye. Thanks so much for your time. We reached the end of today's sessions. We started, as you noticed during the webinar, we started for the basic Zephyr projects. We enable Ethernet support. We monitor link events, configure an IP address, both static and using a DHCP protocol. And finally, we implemented a very, very easy, very simple TCP client to communicate with a server. So hope this webinar gave you a clear and practical overview of how the Zephyr networking stack works and how you can start building your own connected device. Thank you very much for your time and for joining this session. Truly appreciate it. And if you have any questions, so feel free to reach out, write it down at the comments. And when we have some spare time, we're gonna answer your comments that you left in the LinkedIn post. All right. So my name is Diego, and I'll see you on the next webinar.